Hello everyone. Today this is the continuation of atomic structure and this is the last part of our atomic structure lecture. Now today our topic is quantum mechanical model of atom. See, till now we have seen the classical approach of atom, where we have learnt various theories and various probabilities of electrons, where it should lie, where it should rotate, whether it should rotate in a particular orbit. But in this quantum mechanical model, see, in the classical mechanics we have some drawbacks, because in the dual nature and in the Heisenberg uncertainty principle, we have seen that we cannot measure the position and momentum of a particular electron at a particular position at a particular time. We cannot measure both of them. We can measure either velocity or momentum, or we can measure the position of the electron at a particular time. So these are the drawbacks. And another drawback is the behavior of electron in the dual nature. So to rectify the drawbacks, quantum mechanics plays an important role to find out the position of electron at a particular time. It certainly overcomes the limitations of classical mechanics, where they have failed to tell that where should an electron lie at a particular time. So quantum mechanics is a theoretical science which deals with the study of motion of microscopic objects. Let us say in this curriculum we will see the motion of electron, which are both observable wave-like nature and particle-like nature. And it was developed by Werner Heisenberg and Erwin Schrödinger. And his equation, the solution of his equation are actually the position or probability density function of electron, where a electron should lie at a particular time. So Schrödinger described the behavior of electron around the nucleus by a mathematical equation known as Schrödinger wave equation. So where a electron lie, it is described by Schrödinger wave equation. So by solution of Schrödinger wave equation, we can tell where a electron lie at a particular time. Before starting the lecture, I must tell you that this Schrödinger equation, this equation or this equation, they are same equation. Schrödinger wave equation is only applicable for single electron. Again I am repeating, Schrödinger wave equation is applicable for single electron only. So if you are interested to find out the electron density of molecules, then you have to find out the you have to apply the approximate model of or more complex model of Schrödinger equation. This equation, what we have written down in the board, is only applicable for single electron behavior, not for multiple electron. If you want to apply multiple electron behavior, then you have to apply different equation or more modified version of this equation. So see, for a system of such an atom or molecule whose energy does not change, this is an important point, energy should not change for a particular time. For a system of molecule or atom whose energy does not change with the time, the equation is this: H cap psi equals to E cap psi, where H cap is a mathematical operator. This is known as Hamiltonian operator. See, we don't have to focus into this equation in depth, because we don't have this in our syllabus, but you have to know what actually Schrödinger equation is, what it does. what we have interested in this Schrodinger equation is that the solutions, we are more interested in to finding out the solutions of Schrodinger equation which is in our syllabus, but still you have to learn that because this topic is actually in the Master of Science when you done in physics. The solution of Schrodinger wave equation is actually E and psi. Psi is a wave function and E is the energy. Energy related to wave function. Psi is a wave function and E is energy related to that wave function, and this is also known as probability density function because we are interested in to finding the position of electron at a particular time. So this is also known as probability density function. Now see, the actual equation looks something like this. Del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus 8 pi square m by h square E minus b psi, where m is the mass of electron, E is actually your total energy of electron, V is the potential energy of the electron, and potential energy we know Z into E Q1 Q2 by R minus Q1 Q2 by R. So this is Z, E is the charge of proton and E is Q2, let us say, so Q1 Q2 by R, so minus Z E square by R. H is Planck constant and x, y, z are the Cartesian coordinate of specifying direction because the motion is 3D motion, right? Electron will move in a spherical orbit or in any other direction, so we have to specify it in x, y, z direction. And distance and psi, this is psi, this is your psi. Psi is a wave function which represents amplitude of electron wave. That means how far it is from the nucleus. Amplitude of electron wave means how far the electron lies from the center of the nucleus. When the equation solved for hydrogen atom, when this equation or this equation, Hamiltonian operator, this equation, see this is a operator. What is the operator? If you multiply 2 into 3, so multiplication here is a operator. So here H cap is a operator which operates on the wave function, which operates this Hamiltonian operator is a mathematical tool to find out the probability density function or this psi which operates on psi and it gives the solution. That is a very basic concept. Now see, psi is a wave function which represents amplitude of the electron wave. When the equation is solved for hydrogen atom, the solution gives the possible energy states that an electron can occupy. I have already told you the electron can occupy, that means where the electron should lie at a particular time. That is the probability density function, that is the your wave function, and that is the focus of our topic. Possible energy state that an electron can occupy and the corresponding wave function psi of the electron associated with each energy level, because electron, if the electron jumps from lower energy level to higher energy level, then it would have some different position. So for that position the electron would have different energy. The wave function and the corresponding energy states are characterized by a 3 quantum. This is in our syllabus and we will continue this in the next slide, where N, L, M, N is the principal quantum number, this is azimuthal quantum number, and M is your magnetic quantum number. We will see in the next slide. Let us continue our lecture. Now come forward to orbital. What is orbital? We already know about orbit. Orbit is a particular path in which electron revolves, right? We already know from Bohr's atomic model. Now see, what is orbital? It's a region. It's a region in space around the nucleus where the probability of finding the electron is maximum. Just we have discussed about Schrodinger wave equation. From that equation we have already told about that we can find out two values. One value is psi, one value is E, energy. Now psi represents the amplitude of electron. That means from the nucleus where how far the electron lies at a particular time. See, this is the orbit. This is a particular path. Orbit is a particular path. Now what is the orbital? See, electron can lie here, electron can lie here. From the density of electron you can find out very easily that the most dense region of electron is around the nucleus, and if you move far away from the nucleus, the density of electron or the probability of finding the electron is less. Probability of finding the electron is less. So that is the definition of orbital. So orbital is a region, orbit is a path. So see, here I have written down some difference between orbit and orbital. This is important for your exam perspective. It may come in your exam. Orbit do not have directional characteristic. That means it don't have any particular direction because it is rotating in a particular orbit only. But orbital has a directional characteristic because it may distribute in x, y, z coordinate. So except s orbital, all other orbital have directional characteristic. This is the first difference. An orbit can accommodate electron equal to 2n square. So in a particular orbit, let us say this orbit or this orbit or this orbit, in any orbit the maximum number of electron that can accommodate in a particular orbit is your 2n square, where n is your principal quantum number. N is your principal quantum number. That means if the electron lies in n equals to 1, that is in the first orbit, then n equals to 1, if we apply this formula, 2 into 1 square, that is 2. That means in the innermost orbit you can find out only 2 electrons. Let us say n equals to 2, second orbit. If it is second orbit, then how much electron can accommodate in the second orbit? 2 square 4, 4 into 2 8. That means in the second orbit maximum number of electron that can accommodate in the second orbit is 8. Okay, so this formula is extremely important. An orbital cannot accommodate more than 2 electrons. This is a difference. Orbit is a well defined circular path. You can see orbit is a well defined circular path. Orbital is a region. You can find electron anywhere. That is the main characteristics of Schrodinger wave equation. You can find electron anywhere. That's why we use probability density function, because we can find electron anywhere in this region. That's why this is the concept of orbital. Orbit is a well defined circular path. Orbital is a region. Orbit represents planar motion. It is in plane, in a particular plane. Orbital does not specify definite path because electron can lie anywhere at any time. Now move forward to our first solution of Schrodinger wave equation, which is principal quantum number. Now principal quantum number, from very basic I can tell you of sure that, see, principal quantum number is shell, azimuthal quantum number, which is represented by L, is subshell. So you have a shell, and within that shell you have subshell. So it gives average distance of electron from the nucleus, which is n, size of electron cloud or shell. So it is a shell. N represents shell, and energy associated with shell. It is the main energy shell or level in which the electron is present. Let us say if n equals to 1, that means if n equals to 1, that means it represents first shell. If n equals to 2, that means it represents second shell. And see, we have already formulated that in the second shell, maximum number of electron can lie is 8 number of electrons. But in the orbital concept, we have just seen that orbital cannot accommodate more than 2 electrons. If orbital cannot accommodate more than 2 electrons, then how these electrons are distributed in the shell? So you need a subshell where the electron will accommodate themselves. So it is the main energy shell, and if n equals to 1, this represents first shell. See, n equals to 1, it represents shell K, n equals to 2 L, n equals to 3 M, n equals to 4, this is N. We already know K, L, M, N, O, P, Q, R, S, T. It will move like that. Now come forward to azimuthal quantum number. So I have just told you that principal quantum number is for shell and azimuthal quantum number is for subshell. That means within shell we have some subshell. Determines the angular momentum of electron. L is also known as orbital angular momentum, or it has names orbital angular momentum or subsidiary quantum number. Values of L can lie between 0 to n minus 1. This is very important. This is very important. Values of L can lie between 0 to n minus 1. See, let us see some example. If n equals to 1, n equals to, what does it mean? N equals to 1 means shell. If n equals to 1, then we have only one subshell, because if n equals to 1, 1 minus 1 is 0. So 0 to 0, that means you have only one value. So if n equals to 1, you have only one subshell. So for one shell, you have one subshell. Let us say if n equals to 2, that means second shell. If n equals to 2, that means second shell. So n equals to 2, 2 minus 1 is 1, that is 0 to 1. 0 to 1 means 0 and 1. So that means you have two subshell. You have two subshell. One is 0 and one is 1. So here we can see that when n equals to 1, L equals to 0. That means we have one value. When n equals to 2, L has two values, 0 and 1. When, if let us say if n equals to 3, then it will have 3 minus 1, that is 2. That means L will have 0, 1 and 2. That means 3 values. So if n equals to 3, then L would have 3 values. So that means we can say that this represents subshell and this represents shell. So shell is equals to subshell. So we can say number of subshell is equals to number of shell. So let us continue. See, if we have L values something 0, 1, 2, 3, 4, 5 as 0 represents S orbital, 1 represents P orbital, 2 represents D orbital, 3 represents F orbitals, and after that you can continue with the alphabetical order G, H, I. See, here A stands for sharp, P stands for principal, D stands for diffuse, and F stands for fundamental. So S, P, D, F, you have to remember this, the designation of the values of L, 0, 1, 2 and 3. Let us say we have shell, first shell. Let us say we have first shell, n equals to 1. If we have n equals to 1, we have already know that if we have n values, then L values would be from 0 to n minus 1. So if we have n equals to 1, that means 0 to 0, that means L values would be 0. So how to represent this 0 and n equals to 1? How to represent this 0 and n equals to 1? See, 0 stands for S. So we have given S, and it is the first orbital, first orbit. So first orbital n equals to 1. So 0 is n equals to 1 and L equals to 0, represented as 1s. So number of subshell is 1. If we have value n equals to 2, so if we have value n equals to 2, 2 minus 1 is 1, so we should have two values, 0 and 1, 0 and 1. See, 0 is represented as S, 1 is represented as P, and we have second orbital, so 2s, 2p. So we have two subshell, that is 2s, 2p. Now for n equals to 3, 3 minus 1 is 2, so 0, 1, 2, 0, 1, 2. So 0 is S, 1 is P, 2 is D, 2 is D, and we have n equals to 3 shell, so 3s, 3p, 3d. Similarly for 4, you can see 4s, 4p, 4d, 4f. So you have 4 subshells. Remember this, except for hydrogen, the subshells within a given shell differ slightly in energy. It is almost same, but for except hydrogen, all the other atoms and molecules, energy is slightly different. The energy of subshell increases with increasing value of L. This is very important. See, we have 4s, 4p, 4d, 4f. Let us say we have 4s, that means fourth orbital. Shell is 4. Shell number is 4. So increasing value of L. L value, S for 0, P for 1, D for 2 and F for 3. S for 0, P for 1, D for 2 and F for 3. So what is written? The energy of subshell increases with increasing value of L. So here L value is 0, here L value is 1, here L value is 2, here L value is 3. So azimuthal quantum number is increasing. So with increased value of L, the energy increases. That means 4p energy is greater than 4s, 4d energy is greater than 4p and 4f energy is greater than 4d. Remember this formula in order to find out the angular momentum related to L. H by 2 pi root under L into L plus 1. Angular momentum depends only on the value of L, not on n. Principal, it doesn't depend on principal quantum number, it only depends on azimuthal quantum number, because see in the expression you have only value of L. So what does it mean? It means that if you have first orbital S, second orbital S, third orbital S, all of them should have same angular momentum. But see for 2p, 3p, 4p, all of them will have same angular momentum. Okay, so let us continue. Our third orbital magnetic quantum number is ml. It determines the number of orbitals present in a subshell, and more specifically ml represents the orientation of the orbital, how it oriented in a 3D space. See, under the influence of external magnetic field, the electrons in a given subshell orient themselves in the certain preferred region of the space around the nucleus. These are known as orbitals. So if you apply any magnetic field in an atom, the electrons will revolve. Either electrons will revolve either in the clockwise direction or in the anti-clockwise direction. Now we already know that if an electron moves or it rotates, then it will create a magnetic field. If an electron moves or rotates, it will create a magnetic field around itself. Now just imagine if this is a proton, let us say, and electron is revolving. Now electron revolves around the nucleus and itself. Now if it moves around itself, then it will create a magnetic field which will oppose the Earth's magnetic field, right? We already know that Earth has its own magnetic field. Now electron has its own magnetic field. Electron's magnetic field due to movement and Earth's magnetic field will cancel. So some, you can see the some effect is there due to the electron's magnetic field. Now this magnetic quantum number m is its value is from minus L to 0 to plus L, minus L to 0 to plus L, and it has 12 plus 1 values of m for each value of L. If you have given some value of L, let us say L value is 2, let us say L is 2. If L is 2, then see this thing, L is 2, then our m values would be from minus 2 to 0, minus 2 to 0 to plus 2. That means minus 2, minus 1, 0, plus 1, plus 2. We have 5 values. We have 5 values of m. I have explained in this way. Let's see, if L equals to 0, if L equals to 0, then m would be minus 0 to 0 to 0. So that means it is 0. So ml is 0. So that is S subshell has only one orbital, that is known as S orbital. If L equals to 1, if n equals to L equals to 1, then it should have values from minus 1, 0, plus 1. It has, ml has 3 values. So that is P subshell has 3 orbitals, naming plus 1, P0, P plus 1 and P minus 1. We can represent this as Px, Py, Pz according to their orientation in the XYZ axis. always remember Pz value is P0. Z values of L, M is always 0. That means Pz is P0. That is of sure. But Px and Py values are plus minus 1. You cannot say which one is plus 1 and which one is minus 1. It should have a value of a linear combination of plus 1 and minus 1. Always remember this. Pz values, this is the convention. Pz values is fixed to 0. That means 0 represents Pz. That means 0 represents Pz. That is of sure. But plus 1 and minus 1, it don't have some convention. You cannot say that minus 1 is Px and plus 1 is Py. You have to take the linear combination of minus 1 and plus 1 in order to designate Px and Py. If L equals to 2, that means minus 2 to plus 2, I have already explained this, minus 2, 1, 0, plus 1, plus 2. 5 values. That means D subshell have 5 orbitals. We will see the 5 orbitals and the structure of the 5 orbitals in the next slide. It has value dx square, dy square, dz square, dx square minus y square and dz square. Now see, if L equals to 3, ml, if L equals to 3, that means ml value would be minus 3 to plus 3 and including 0. That means minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. We have 7 values. That means for F subshell, we have 7 orbital. Now move forward to our last quantum number, which is our ms. Now as electron move, see, electron can rotate from in the clockwise direction and in the anti-clockwise direction also. So for clockwise direction, we represent m as plus half, that means ms value is plus half, and for anti-clockwise direction the ms value is minus half. For anti-clockwise direction ms value is minus half and for clockwise direction ms value is plus half. If you want to find out the spin angular momentum, then you can use this formula. So to summarize the whole thing we have learned throughout this lecture, see, n is, the main thing is n is shell, L is your subshell. So that means within a shell you have subshell. L is your orientation of the orbital. See, why orientation? Because Px, Py, Pz, we will learn in the next slide that Px, that means is represent a dumbbell structure in the x-axis and y-axis, z-axis, something like this. So L is the orientation of the orbital, how it is oriented in the 3D orbital, and ms is spin, clockwise spin and anti-clockwise spin. So these 4 quantum numbers, by these 4 quantum numbers we can explain everything in the atomic structure. So let us continue our lecture. This is Pauli's exclusion principle. It states that no 2 electrons in an atom can have same values for all the 4 quantum numbers. Let us say we have n values as 1, L0, N1, L0, M0, M0, but angular, the spin quantum number would be different. See, here S has plus half, here S has minus half. So that means we can conclude here that this leads to a conclusion that an orbital can have maximum of 2 electrons. This is the most important conclusion of Pauli's exclusion principle, that orbital, any orbital can have only maximum of 2 electrons. That means in A subshell, in the previous slide we have learned that we have 1 orbital. For 1 orbital, each orbital can have 2 electrons. So for 1 orbital we have 2 electrons. P subshell has 3 orbitals, that means it has 6 electrons. D subshell has 5 orbitals, then it has 10 electrons. F subshell has 7 orbitals, so it would have 14 electrons maximum. Now let us see the diagrams, the boundary surface diagram of S orbital, P orbital and D orbital. If we consider shape of S orbital, it is non-directional and spherically symmetrical. See, if we consider 1s orbital, the electron can distribute in the spherical manner, So there is a sphere. If we have 2s orbital, always remember between 1s and 2s, this is 1s orbital, spherically symmetric. 2s orbital will also be spherically symmetric, exception is that the radius would be large. The radius would be large. So that means the electron density is here, and there is a gap. In this gap there is no electron. If there is no electron, that means we can say probability of finding electron in this region is 0. So this region where probability of finding electron is 0 is known as node, or it is 0 probability and known as node. So for 2s orbital we have one node where no electron can be found, then again we found electron. For 3s orbital the structure will be something like this, right? We have two nodes. We will have two nodes where no electron would be found. Here for 2s orbital we have one node where no electrons can be found. For 3s orbital we will have two nodes where no electron would be found. Now shape of p orbital, we already know px, py, pz. So if we consider 2px, 2py and 2pz, this is known as a dumbbell shell. Dumbbell structure. Dumbbell, see here is two dumbbell structure. So for 2px, that means it is lying in the x axis. For 2py it is lying in the y axis. 2pz it is lying in the z axis. Always remember, all these dumbbells have equal energy but orientation is different. If we consider the shape of d orbitals, the shape is something like this. This is dxy, that means the dumbbells are lying in the xy plane. This is yz, this is zx, this is dx square minus y square, and this is dz square. In dz square we have a ring. We have a ring in between the dumbbells, of the d orbital. Now see, remember one thing, that dxy and dx square minus y square are same with 45-degree rotation. If you rotate dxy in 45 degree, then you will get dx square minus y square. That is the point you have to remember. And in the dz square we have a electron cloud, or we have a ring in the in this z axis. Now in an orbital, always remember, total number of nodes is n minus 1, angular nodes is l, and radial nodes would be n minus l minus 1. So that's all for today. In the next class we will see energy level diagram in the atomic structure, and we will see boundary surface diagram from the perspective of Schrodinger wave equation, how we are coming to these conclusions, that where the electrons will be found out. Remember one thing, that in the dumbbell shell or in the shapes of p orbital, the maximum number of electrons can be found out in the last of the dumbbell. Here the electron density is maximum. That's all. We will continue our lecture in the next.